to see you. We are recording these talks today, and today I welcome you in the name of Emily and myself to the second Beyond EPICA Ice Core Fall seminar series. Last time in September, in case you were there, we talked about and heard about CO2 reconstructions during the mid-Pleistocene, and this time we will switch a little bit and we will talk about modeling efforts on the mid-Pleistocene transition. And we were able to invite two very interesting speakers, Matteo Willeit, who works at the Potsdam Climate Research Institute, and Axel Timmerman from the Pusan National University in South Korea. And both have, I think, published landmark papers and done landmark work on modeling the mid-Pleistocene transition. And I'm quite curious to hear about all these details from themselves. Like last time, we will have the two talks, each of 20 minutes. Then we will have the possibility to have some direct question afterwards. And at the end of this 1 hour, we hopefully can then maybe have still some time to have some more discussion and questions for people who like to do so. But we will start today with Matteo Willeit. And let me just give you a short introduction in case you haven't met Matteo. Matteo studied physics, as far as I really informed in Bologna. Matteo, please correct me if this is wrong, but this is what I found from you, that you are a physicist and you were interested in your physics studies already in climate physics and meteorology. And from 2011 on, you have been at the PIC Institute, the Potsdam Institute. You did your PhD there first, looking at vegetation climate interactions and also carbon cycle feedbacks with the climate model. So the climate model, as we will hear later on, is a model of so-called intermediate complexity. And then you also worked on deeper times, like the Pliocene-Pleistocene transition and also the mid-Pleistocene transition. And now you're also working on the last glacial cycle, for example, in the framework of the German Palmer project. And nowadays you stayed at PIC, and nowadays you're a senior scientist there. Yeah, by this short introduction, Matteo, I would stop my screen sharing and give the screen to you, and the floor is yours.
Thanks, Martin. Thanks a lot for the kind introduction. Good afternoon, everyone. So let's start sharing.
Yep, I can see it.
Great. Yeah, so today I will talk about the mid-Pleistocene transition, but from an Earth system modeling perspective. Okay. So looking basically at the last 3 million years here, I'm a modeler, so time goes from left to right. I hope that's okay for most of you. Yeah, so most of the information we have about climate evolution over this quaternary time period is, or the most reliable information on global climate evolution is definitely from Benthic Delta 18O records, which are a proxy for deep ocean temperature and ice volume on land. And what they show is basically a long-term trend, a long-term cooling trend with increasing variability, going from 3 million years ago to the present. And also remarkably, there's a transition around 1 million years ago from glacial cycles dominated by a 40 kiloyears period to longer and more asymmetric glacial cycles with a periodicity of around 100,000 years. And the question is obviously what caused this transition? And we're trying to use an Earth system model of intermediate complexity, in particular Climber-2, to try to address this question and to understand a bit what processes were at play in this transition. And Climber-2 has a relatively coarse resolution climate model, but it's coupled to a Northern Hemisphere ice sheet model, and it has a global carbon cycle model, which allows it to simulate CO2 in the atmosphere interactively. And what Ganopolsky and Brovkin have done in 2007, so 5 years ago now, they showed that the model can simulate reasonably well the evolution of climate over the last 400,000 years when driven only by changes in orbital parameters, which is shown here on top, represented by the maximum summer insolation. And below you see the model response in terms of sea level compared to reconstructions and CO2 compared to ice core data. So considering the complexity of the problem, this is quite remarkable, I would say. And what we did then, we tried to extend this to the last 3 million years. So here is the corresponding insolation or the orbital forcing extended back to 3 million years ago. And this is what the model does when forced only by changes in orbital parameters over this time period. And what you see is that, well, the model simulates strong asymmetric 100 kiloyear cycles over the whole time period, basically. Same for CO2. But this is clearly not in good agreement with the Delta 18O record, which shows much, differs quite substantially prior to 1 million years ago. It has to be mentioned that recently some modeling efforts showed that the orbital forcing could have played a role for the MPT, but I think this has still to be confirmed. And what is clear is that Climber 2 does not show this. So orbital forcing is definitely not enough to simulate climate evolution over this time period in agreement with observations. So we went and looked for prominent hypotheses that were put forward to explain this transition. And one of them is definitely the regolith hypothesis, which basically postulates that sediment removal by glacial erosion played a role for ice sheet dynamics, stabilizing the ice sheets through time. This hypothesis was first described by Clark and Pollard in 1998. But it's noteworthy that they recently kind of retracted this hypothesis. Yes. And then more recently, this was kind of extended by Ganopolsky and Kalov by also including the effect of glaciogenic dust produced by the ice sheet sliding over the sediments, which would then produce airborne dust around the ice sheet margin, and that would be deposited on the ice sheets and would reduce surface albedo and therefore affect surface mass balance of the ice sheets. So the idea of this regolith hypothesis is that if you look at present-day distribution of sediments over the Northern Hemisphere continents, you see that large areas of the continents are depleted in sediments. So there's areas which have basically exposed bedrock, hard bedrock. And this is thought to be a result of the glacial erosion by ice sheet over the quaternary by glacial cycles. And so if we assume that this is true, then we can assume that in the Pliocene or before 3 million years ago, continents were largely covered by sediments, which would then have been removed by ice sheets over time. So what we did in Climber 2, additionally to orbital forcing, we prescribed time-changing sediment mask, reflecting this evolution of the regolith cover over the continents. And what the model produces with this combination of forcings is then, it does produce a transition from 40 kiloyears cycles to 100 kiloyear cycles in quite good agreement with oxygen isotope, with the wavelength spectrum of oxygen isotopes. But what it cannot capture is this long-term trend, this long-term cooling trend, which is also seen in sea surface temperatures, for instance. So how can we explain this long-term cooling trend, which is seen in different proxies? And one is a possible long-term decrease in CO2, which is reasonable, considering that it's widely accepted that CO2 was higher during the Pliocene. But then what is much less clear is how this transition or how this decline in CO2 occurred, over which time. But the timing of this decrease in CO2 is of course crucial in order to understand whether it played a role in the mid-Pleistocene transition or not. There's obviously also possible other factors like other greenhouse gases could have contributed, but this is not something that we are considering in our study here. So this is a figure illustrating or summarizing what we know about CO2 evolution over the last 3 and more million years, time going from right to left now. So what we definitely know quite well is the last 800,000 years from the EPICA ice core. But beyond that, things become a bit more uncertain. But it seems that CO2, there is some indication that CO2 was higher during the early Pleistocene. Looking a bit more closer at really at the time period around 1 million years ago, where we had this transition, there's this recent reconstruction of CO2 by Yamamoto, showing that CO2 was possibly lower during interglacials before the MPT, which is very interesting, but in some sense also hard to reconcile with other data. So yeah, so what we did in Climber 2, we prescribed a decrease in volcanic outgassing over time. It's a relatively small decrease by 10% or so. And this will then be reflected in the CO2 simulated by the model. So with orbital forcing and volcanic outgassing decrease, this is what the model produces. So on top again, delta 18O. And you see that the long-term trend and the change in amplitude of the cycles is definitely better reproduced than it was before. This decrease in CO2 also results in a change in a transition from 40 kiloyear to 100 kiloyear cycles, although it's not as clear as for the regolith. But yes, in terms of sea surface temperature, for instance, this agrees much better with data. And you see the CO2 scenario here, which goes from roughly 350 ppm decrease to less than 300 during interglacials here. So it's not a very big decrease, but has quite substantial impact on the climate ice sheet evolution. So we then combine these two forcings. So we prescribe both changes in sediment mass and decrease in volcanic outgassing. And we created some scenarios for this and then used root mean square error or best fit to try to best match observations and model, observed and modeled delta 18O. And we then ended up with the best scenario, which is shown here on the left by the thick lines. And in terms of simulated delta 18O, this is then what the model produces in blue here compared to Willeit and Ramos stack in black. And you see it's doing a quite reasonable job at reproducing many of the features of this curve, except for some time periods where the model has some problems, like around miss 11, where the model is just not responding to the relatively weak orbital forcing, indicating that possibly the model is still not nonlinear enough to reproduce this strong nonlinear response during glacial terminations in particular. And if you look at the power spectra of this time series, then you see clearly that before the MPT, the 40 kiloyear cycles dominate in the model in agreement with data. The model shows also some response at the precession bands, which is not seen in observations for some reason. Then we have the transition period where both 40 and 100 kiloyear cycles are there. And then you have the dominance of the 100 kiloyear cycles over the last 800,000 years. What we can do, we can also separate the benthic delta 18O signal into deep ocean temperature and sea level components. And in particular, looking here on the left at the variability of the delta 18O curve and how it changes over time, which is shown here by the running standard deviation of the Willeit and Ramos stack in black, and compared to the modeled evolution in the gray shading. And then you can separate temperature effect in green and the sea level effect in blue. So you see that initially the temperature variability dominates the delta 18O signal, but then after the MPT, clearly the large sea level variations become dominant, and also the contribution of deep ocean temperature decreases, partly because simply the glaciers are already too cold, so the deep ocean is already close to the freezing point, so it's kind of a saturation effect. You can't get much colder than that. Yeah, and similar is shown here on the right, just that the ratio of the two. So temperature is more important initially, and then sea level takes over. And some more results for this best scenario. Here is shown sea level on top, simulated. So you see this increase in ice sheet thickness or ice sheet volume during glacial maxima, and also the transition from shorter cycles to longer cycles. This decrease in CO2 that we have already seen, and the corresponding global cooling seen both in sea surface temperature but also in global temperature. In terms of simulated ice sheet extent, the ice sheet maximum ice sheet extent is larger after the MPT than before the MPT, and also ice sheets are generally thicker. And after the MPT, the ice sheet extent and thickness is actually quite comparable to, for instance, here the extent of at the LGM from reconstructions in the solid white line. Yes. So to summarize somehow, the model produces 100 kiloyear cycle only for relatively low CO2 and for the present day sediment distribution. While if CO2 is higher than 40 kiloyear cycle dominate independently of the sediment distribution, and also if sediments cover the whole continents, then 40 kiloyear cycles dominate irrespectively of the CO2 concentration. So we propose that this transition, this MPT transition, or in general the evolution over the last 3 million years in terms of climate, went from high CO2 and sediment-covered continents, resulting in a 40 kiloyears world, and this transition somehow in this phase space of sediment mass and CO2 to the larger asymmetric 100 kiloyear cycles of the last million years. And recently we have also found that Climber 2 exhibits self-sustained oscillations under a range of boundary conditions, which is also quite interesting. And if you're interested in more details, then we have a paper in discussion in Earth System Dynamics by Takahito. So summarizing, and so that relatively simple IMICs allow to realistically reproduce quaternary climate variability, which is not obvious in a sense, considering all the processes involved. But the rule of regolith and CO2 for the MPT, they remain uncertain, and there are several reasons for that. And this highlights the importance of reliable CO2 reconstructions from beyond EPICA. So we need longer reliable CO2 reconstructions to really see how that CO2 changed across this transition. Also for the regolith hypothesis, what is really important is how the sediment sliding is parameterized in the ice sheet model, and how this depends on the bed, so whether it's soft sediments or hard bedrock. And this is very uncertain and unconstrained simply because we don't really have observations of big northern hemisphere ice sheets at present. And there's some laboratory studies that are looking at that, and there's possibly some consensus emerging, but this definitely remains an uncertainty. And similarly, the role of particularly of glaciogenic dust in glacial cycles is also difficult to quantify. Again, because we don't have big ice sheets at present in the northern hemisphere, and we can't observe this dust if it is produced or how relevant it is for surface mass balance. And these are two things that will be difficult to constrain also in the future. So some uncertainty will remain. But I think that to make some progress in understanding of the MPT, what we need is really to combine and integrate the different strengths of models and data, possibly new models, new data. And Axel will after this talk describe one way of going with more complex models like fully coupled GCMs. And yeah, on the data side, definitely CO2 records from ice cores extending back into the past would be a very useful addition to this. And what we are doing on our side is we have in the recent years developed a new model, ClimberX, which is a bit higher resolution than Climber2. So it's 5 × 5 degree horizontal resolution in all climate components now. It has a fully three-dimensional ocean, statistical dynamical atmosphere model, dynamic thermodynamic sea ice model that's coupled to 2 ice sheet models, which can be applied to different domains. So we also have Antarctica now. We can simulate many different ice sheets at different resolutions for more details. We also have a solid Earth model that computes the glacial isostatic adjustment and relative sea level changes, so to get also some spatial pattern in sea level changes. We have a land model with dynamic vegetation, and we have the hammock model from the MPI in Hamburg, state-of-the-art ocean biogeochemistry model included, with marine sediments also, which again allows us to compute interactively the CO2 concentration in the atmosphere. The model is a bit slower than Climber2, so it's about 10 times slower, but still integrates something like 10,000 years in one day. So we hope to make some progress also in the understanding of glacial cycles in general, and more specifically the MPT with this new tool. Yeah, and this is just an animation showing the last glacial inception simulation with ClimberX, starting from the Eemian. So if I play this, you see that corresponding to the decrease in summer insolation, you have an expansion of sea ice indicated here by the white area. You have a southward shift of the tree line indicated by the green shading over land. This causes a strong vegetation feedback, albedo feedback, which allows then the ice sheets to develop. This is interactively simulated here, which then affect the AMOC and so on. Yes. And well, the climate component of ClimberX is open source, and we hope that the rest will also become open source soon. We have some license issues, but so yeah, if anyone feels that this could be useful for the comparison with data or whatever, I'm happy to yeah, just get in contact. And with this, I leave you, and I'm happy to take questions.
Speaker now.
Thank you,
Matteo, for your talk.
Yes, so now I would like to introduce our second speaker, Axel Timmerman. Thank you, Axel, for talking to us. So Axel conducted his PhD research at the Potsdam Institute of Meteorology in Hamburg. And after a postdoc in Netherlands and a research leading position in Germany, he moved to the University of Hawaii, first as an associate professor and then as a professor. And since 2017, is the director of the IBS Center for Climate Physics at Pusan National University in South Korea, where he's also a distinguished professor. And so, as many of you know, Axel is a climate physicist and oceanographer, and he has a very wide range of interests, going from climate dynamics, ice sheet modeling to human migration. And he has received numerous prestigious distinctions for his research. So we're very happy to have him today to give this talk, where he's going to tell us about simulating the global climate beyond EPICA. Axel, please.
Thank you very much, Emily, for this kind introduction. Can you hear me well?
Yes.
So I just got a little text message from Hubertus Fischer, who joins the meeting, and he said it should be beyond EPICA. So I added this second beyond here. But the main point is we would like to essentially extend the simulations that Matteo was presenting with a coupled general circulation model. And of course, it's impossible still to do that with ice sheet and carbon cycle fully coupled. But we wanted to do the first step to essentially use the Climber simulation as a forcing for a state-of-the-art coupled general circulation model, and that will be the CESM1 Community Earth System Model version 1.2. And this is work done in collaboration with Matteo Willeit and Andrzej Ganopolski. Most of the work was conducted by Kyung-Suk Yoon, who I would like to acknowledge here. Okay, so the forcing that we are using is the ice sheet forcing and the CO2 forcing from the simulation that Matteo just presented, covering the last 3 million years. And you will see many time series today that cover this time period, and most of my slides also show time going from left to right. And of course, in order to force the climate model, we also need the orbital forcings. So this is included. We have obliquity, eccentricity, and precessional forcing. We use the Berger forcing. Maybe we should have used the Lasker forcing because there are deviations prior to about 1 million year that may actually play a little bit of a role. Also, we had to make some estimates for the N2O and the methane forcings. I will just describe that in the next slide. Let me just move that over here. Okay. The CSM 1.2 model was used in a T31 resolution, which corresponds approximately to 3.8 degree resolution in the atmosphere and about 3 degree in the ocean. And we're using the orbital acceleration technique that was introduced by Stefan Lorenz and Gerrit Lohmann many years ago, and the entire model simulation is not 3 million years long, but it's only 600,000 years long. So what we do is we squeeze essentially all the orbital scale forcings, so greenhouse gases, orbital forcing, and the ice sheets by a factor of 5. Otherwise, it would be still impossible to conduct these simulations. And what's also important, you will see that in order to conduct such a simulation, we need a supercomputer for essentially an entire year. And this is still only possible if we split up the simulation in different time slices that we actually run in parallel. There is no way currently with the coupled general circulation model to run the entire stretch sequentially from 3 million years all the way to now. So we split up our simulation in these chunks, and each chunk starts from an interglacial, runs through a glacial with acceleration factor 5 into the next interglacial. And in this next following interglacial, we have a little bit of an overlap period so that we can assess certain spin-up effects in this overlap period. So this has been used early on by my colleague Tobias Friedrich and we ran the Lufglim Earth System model of intermediate complexity for 800,000 years, again with a very similar type of modeling approach. Okay, so coming to the forcings, CO2 forcing was already shown by Matteo. And we made very simple assumptions here on the methane and the N2O, which are essentially statistical fits of the existing EPICA data to the benthic delta 18O, Lisek and Ramo data set. The correlation is not super high for N2O. As we know, there is a lot of millennial scale variability, but this is essentially just a way of extending the forcing back in time. And I think it doesn't matter that much because these two forcings are relatively small and they don't play a large role actually in our simulations that I'm going to show to you. Again, yeah, forcing is clear. Then the model simulation covers 600,000 model years, and keep in mind we have a large amount of data, about 0.5 petabytes of data that was generated and is available actually for everyone to analyze. We have a subset of these data actually on our climate data server, and you're welcome to look at those, and I will show you soon how you can access this data server. Again, 30 million CPU hours is quite a large chunk on our supercomputer Aleph, which has about 1.5 quadrillion calculations per second. Okay, so just if you are interested in these data, you're welcome to analyze them. We have a climate data server in our center, and you can either access the data as opened up, which is very convenient for MATLAB, Python, and all sorts of analysis software, or if you're not familiar with NetCDF data, you can also click on LAS, Large Live Access Server. There you have a screen. You can focus on your preferred region, pick out your favorite sediment core spot, and extract the data directly, and it generates automatically on the web interface the time series. You can export stuff into Google Earth and so on and so forth, make some fancy animations in Google Earth later on. So I will show you later on how that works. So we have several projects, and maybe the most important one regarding this presentation today is that we looked at many different global features in the climate system, and much of this has been described in our recent Climate of the Past paper. I think it's not fully formatted, but you can already download the final version. By Kyung-Suk Yoon, and there we are looking at the typical global mean temperature, how does El Nino respond, what does the heat transport do, and so on and so forth. So the typical type of presentation paper. But we published already parts of this simulation in earlier studies where we looked at human habitats. So we have a study in Science and in Nature, and another one in Science. And each of them looks at different aspects of these transient simulations in the context of human evolution. We also ran, or my PhD student, Elke Zeller, she ran the Biome 4 model using the climate output from this 3 million year CSM simulation. And also this was published in Science, where we look also at the favorite biomes that early humans evolved in. We're working currently on another paper that looks at tropical climate, monsoon systems, and ENSO. And we have another project that looks at 2,000 mammal species on our planet and how they have responded to past climate change over the last glacial cycles. Okay, so this is essentially the scope of projects that we are currently embarking on. You saw already the Willeit forcings up here. The global mean surface temperature response of the coupled general circulation model, CSM, is shown here in black, and you can compare it directly with Matteo's simulation. I should mention also one of the motivations was to get a full three-dimensional model simulation. Keep in mind that the Climber model, the earlier Climber 2 model, has a two-dimensional ocean and is still relatively coarse resolution atmosphere, which does not simulate large-scale Hadley circulations, monsoon systems very accurately, and it doesn't have any El Nino variability and so on. So this was really one of the motivations to dig much more into the physical mechanisms that also govern tropical climate dynamics, and that's why we switched to the much more expensive CSM model. Okay, and you can see both of them actually seem to have a very similar climate sensitivity, and we have another global mean surface temperature reconstruction. Most of the amplitudes are captured quite well, except for some of the interglacial periods, which according to the proxy reconstructions for global mean surface temperature are even larger. But keep in mind, we have a similar climate sensitivity in this model compared to the Climber 2. Okay, another nice comparison is here with the tropical temperatures extracted at certain sediment core locations. And the nice thing is that Timothy Herbert generated a tropical SST stack from alkanones for several different locations, and that's shown here in green. And it also shows this long-term cooling trend and this wonderful, rather rapid transition from the 41 kilo-year world to the 80 to 120 kilo-year world. And this is something that the model captures quite nicely. I have to say, keep in mind that the mid-Pleistocene transition in our model is actually a response to Matteo Willeit's and Andrzej Gonopolski's climber forcing. So we are not solving the MPT problem. We are using the solution from Matteo and Andrzej as a driver essentially for our climate model, and our climate model has a much more realistic representation of global climate dynamics, and that's why we're using it. Okay, we can also compare monsoon records. There is the famous Sanbao cave reconstruction Delta 18O, which is a proxy actually for more southern Chinese, maybe more Indian monsoon records. And we can also see beautiful amplitude, eccentricity amplitude modulated precessional cycles in line with these records. So we can go through many, many slides, and I have given another PMIP Wing seminar where I did this. It's kind of interesting to see how well the model actually works, but there are areas where it does not work. And here is an interesting example. Again, I'm showing the tropical SST stack that I mentioned earlier on from Herbert, and the cooling trend in the model is nicely reproduced, which also supports the CO2 decrease that Matteo suggested for his simulations. You can see other records in SST that are coming out quite nicely. But then, interestingly, if you go to other areas, you don't see in the proxy records this strong cooling trend. They seem to be much more stable. They look much more like the very early simulations that Matteo conducted, where the CO2 did not have that strong long-term trend. So there are still some interesting things to resolve. Not everything comes out correctly, but the long-term cooling trend is definitely something that one needs to reconcile in some of these proxy records, because the model clearly has it, but the proxy data don't. Okay, of course, no climate model simulation presentation talk should forget the AMOC. So that's a critical variable, of course, but this is the solution that we have. So the model generates mostly obliquity and precessional scale variability, but also the model itself, CSM, for certain parameter configurations, orbital configurations, actually has a nice millennial scale variability as well. I don't call it Dunsgaard-Oeschger cycles. I think the word is overrated here, but definitely we have internal millennial scale variability. And one has to keep in mind that we do not apply the freshwater forcing from the ice sheets here as a forcing for the transient run. And there are several reasons for it. We are currently testing this by using the freshwater forcing from the ice sheets directly as a forcing also for the CSM model for the last 125,000 years to see if it actually makes sense. And but this is, I wouldn't trust the AMOC as something very realistic, because we know, of course, there were much more millennial scale freshwater pulses in the system, such as Heinrich 1 and Heinrich 3 and Heinrich 4. All of them are kind of missing. As we can see, the AMOC only varies between 15 and 25 Sweatrop, whereas from the protactinium thorium data, we know that the AMOC was probably much weaker during certain millennial scale events. But anyways, this is what the model shows for these particular configurations in the forcings. Now, going to the beyond EPICA or beyond EPICA, let's go a bit more to the southern hemisphere. So we are looking here at the evolution of westerlies. Again, the black time series from the CSM model. And these are some reconstructions. And of course, dust is not only westerlies, but at least is affected by westerlies. And here, this is data from Frank Lamy. The interesting thing I wanted to point out here is that there is quite a bit of a precessional scale variability in the westerlies. So we're looking at the strength of the 500 hectopascal zonal winds in the model in comparison to some of these proxies. Is not a great comparison, but what we see is actually there is a pretty nice, very robust precessional cycle in the westerlies. And that's kind of different from a paper that I wrote several years ago where we used the Lovegley model, and there clearly the obliquity cycle seems to dominate the CO2. So things can change, and also I suppose this is more realistic because it's a full coupled general circulation model. Well, westerlies, we can also just define the northern annular mode and the southern annular mode. And what you see is both of them are actually strengthening. That makes sense because we're cooling down, and we're cooling in particular in high polar regions. So that intensifies the baroclinicity. So overall, the westerlies intensify. But if we look at the frequency here in a wavelet spectrum, clearly the southern hemisphere westerlies, the southern annular mode, has a precessional cycle, whereas the northern hemisphere has actually much more of a mixed obliquity precessional signal. So this could be interesting later on for understanding also moisture transport towards the ice sheets and so on and so forth. So there is a lot in each of these figures, and in 20 minutes I can't explain all of that, but just to give you an overview what's going on. Well, this model is interesting because we can use the same configuration also to run it into the future. Here you can see the last 3 million years global mean surface temperature, and then of course heavily stretched the next few hundred years following certain scenarios. Here we just use RCP scenarios. But what you can clearly see is if we ask the question, well, according to our model simulation, the present day climate, would it have been, is it higher in terms of global mean temperature than the last 3 million years? And the answer from this one is yes. So according to this model simulation, we have no point in time where at least the trends exceeded those of the last 3 million years. If you look at the rate of change, temperature change, and this is logarithmic here, you can see we are 2 orders of magnitude more in terms of the temperature rate of change compared to anything that we have seen in the last 3 million years. Well, that's kind of clear. But anyways, it's good to see this, that we are really interrupting the system in a very unprecedented way. I wanted to talk about other applications, not about the human stuff and mammals, but about a simulation that we conducted with an ice sheet model. And you wonder, why do we do an ice sheet model? We just used the ice sheet forcing from Matteo. But the interesting thing is Matteo's simulation does not include Antarctica. And we wanted to use the climate model simulation, CSM, 3 million years, and drive a biohemispheric ice sheet model, first to see how much of Matteo's forcing in Psychopolis can we actually reproduce in the northern hemisphere, but then also to generate a new simulation that's independent of the climate forcing, independent of the climate ice sheet forcing for Antarctica. And this is where we get into the Beyond EPICA part. So we use Penn State ice sheet model in both hemispheres, and the simulated total ice volume here in both hemispheres is shown in red. Northern hemisphere is also the smaller red, and then Matteo's simulation is the gray. So there it looks very similar, which is kind of clear because Matteo's ice sheet forcing changes the temperature. That temperature drives our ice sheet. So it's not too surprising. But what's new is really the behavior of Antarctica, because that was not included. Okay, let's take a look more at Antarctica. Here is the simulation of the last 3 million years, and it looks a bit interesting and surprising. So we are getting now, this is in kilo years. So we are now getting into the MPT, and you see the flickering of the main ice shelves is starting to decrease, and we have a much more stable system. So if we look at the last glacial maximum, for instance, it will be somewhere here. Sorry, let's say somewhere here. You can see that the ice sheet moves almost all the way up to the continental margin. We have very small shelves left over. But what's important is actually that, and it's very difficult to get in a climate simulation, that if you run transiently an ice sheet model for 3 million years, it's not trivial to get all the ice shelves at the right with the right configuration. So here, Ross ice shelf. Well, we have a little dip in here. The Weddell looks actually much better. Emery ice shelf, we have some funny hole in there. So there are still things that probably need to be fixed in some way with bias corrections. But anyways, this is a useful simulation, which can actually be used also later on for age modeling of ice cores, because we can introduce also an age tracer. Looking at the Southern Hemisphere Antarctic ice volume time series, you can see, wow, there is a pretty dramatic MPT threshold here. And there is definitely the forcing in the CO2, but the ice sheet actually in Antarctica responds much more strongly. So we see there is this really drastic transition around 900,000 years. So this is a marine isotope stage 22, where the system suddenly jumps into this completely different state. So clearly, the Penn State ice sheet model has a threshold to the forcings, even though the forcings do something similar but less abrupt. Okay, looking at this little dome C, I was wondering what are the elevation changes on Little Dome C for Beyond EPICA. And what we see here is, just move that over, what we see are variations in the height, simulated height over the last 3 million years. And what's interesting here is that the height change over Little Dome C would be in the range of about, I don't know, 100 to 200 meters. That's kind of similar to what Valérie estimated in 2010 for EPICA Dome C itself. So the range of variability is kind of similar. This is important also to interpret the lapse rate driven temperature changes that contribute to the reconstructed temperatures. So temperature over EPICA, in this case, nearby Little Dome C, is, as I mentioned, is very similar to EPICA for the last 784,000 years. And prior to that, it's very much driven by the CO2. And hence, we have still a strong precessional and obliquity cycle, because Matteo's CO2 forcing has quite a bit of precessional forcing, which, by the way, is absent in some of the tropical SST records. So there is a big question mark. Are we going to have less CO2 if we go back, less precessional variability if we go back with Antarctic ice core reconstructions or more? Okay, so Northern Hemisphere, again, is interesting because we ran bihemispheric. We have the reconstructed ice sheet also in the Northern Hemisphere, and this pretty much follows the Climber 2 ice sheet forcing, because we use the same temperature variability, but there are actually some important deviations. And one of the key features is also that this model has ice shelves also in the Northern Hemisphere, and you can see very often these ice shelves between Greenland and Iceland and so on, being there for some time, disappearing quickly. So there is a lot of interesting dynamics that is not fully captured in the Climber 2 simulation. And also, if you just look through the evolution, here we are building up, for instance, the Laurentide ice sheet quickly. The Eurasian ice sheet starts to build up, but it disappears very quickly. So usually we have the Laurentide ice sheet being the kind of flywheel in the system, or the large inertia, whereas the Eurasian ice sheet is much more flickering and contributing to the precessional scale variability in the freshwater forcings. So that's important, and I think I'm running pretty much out of time here. Am I running out of time, Emily?
Yes, you are.
Okay.
You can take a couple of minutes and you can conclude.
Yeah, so I wanted to say one other thing regarding this MPT transition. I mean, this is a fascinating time period, just from a human evolution point of view. Around, now time goes the other way around, around 1.8 million years, Homo erectus kind of came out of Africa. Then they kind of hung out in Central Europe, Italy, and so on. But then it looks like there is some kind of hiatus here, and everybody was wondering what's going on and so on. Is it a hiatus, or has nobody found anything there, and so on? Anyways, if you look just at the normal benthic delta 18, oh, it looks like there is not that much going on. Marine isotopes stage 34 does not look very much pronounced. However, there are new sediment cores from the Shackleton side of the Iberian margin that my colleagues, and I saw John was also joining the Zoom call. So he analyzed the Alkanone SST, reconstructed Alkanone SST for that time period. And the remarkable thing is that there is one time period, and this is Jean's data, and we have also pollen data from Vasily Margari, where the temperature drops dramatically. So 1.126 million years ago, we have a drastic drop of about 7 degrees near the Iberian margin, and the vegetation changes essentially to steppe point. So there is a huge kind of millennial scale event. It lasts for about 4,000 years, and this is happening right inside MIS 34. And we wanted to know which effect would that have on human habitats. So again, we use all the fossil records of Homo erectus and tools and so on, and we built a habitat model using this CESM 1.2 climate model, and we combine these two, and then we ran an additional freshwater forcing experiment that mimics this 4,000-year-long rapid terminal stadial event here. And this would be kind of the result. So here you see the simulation temperature over Spain, and this is with a freshwater forcing that is applied during MIS 34 that matches kind of the magnitude that we could estimate from the Shackleton side marine sediment core. And so you can see this is a really strong cooling here relative to anything that the orbital forcing can do. Of course, later on, there were other millennial scale events which are not included here. But you can clearly see this could have been really a trigger point for a depopulation event in Europe. And that's what we're suggesting in our science paper. So, of course, if anybody finds something with a very well-dated fossil around 1 million years ago, I think our paper has a problem. But that's definitely something we are waiting for to have a proof of falsification of our idea. Anyways, this just tells you orbital scale variability is not the only thing that we need to worry about, but we really need to also capture these millennial scale events. And we're getting some amazing high-resolution Alkanone data from many of the records nowadays that can capture this millennial scale variability and the onset that also started around the MPT. So this is something to keep in mind. Ice sheets became larger, but also the millennial scale variability became much larger, and that's relevant for ecosystems as well. So I think I'll just stop here. Thank you.